Eric Burgess here, and today we are doing a hypothesis test. We have this statement, this question. A firm claims that kids ages 0 to 2 spend an average of 29 hours per week in care not provided by parents. A study was conducted with a random sample of 30 infants, and it was found they spend an average of 32.3 hours per week in care not provided by their parents. The population standard deviation is 3.5 hours. At an alpha of 0.01, is there sufficient evidence to conclude that the sample mean differs from the national mean? So we have a clear case of a hypothesis test. We can tell, besides the title, if you were just given this on a test, you could tell it is because we have a claim here. And then there was a study conducted to see if that claim was true. So we immediately know that we're dealing with a hypothesis test. We're going to do it with three methods. First, we'll do the formula method. Then we'll use the calculator. And then we will use Excel. So let's go ahead and just dive right in. All right, so first thing I like to do is I like to go through and actually get all the values out of the problem. So we've got a firm claiming, so we've got our claim here, so that's important. So our claim is always H naught and then H1, or some teachers will write HA. And this is for the null hypothesis, H naught. And then we have the alternative hypothesis, which is where the A comes from, or we just sometimes call it the first other hypothesis. You know, there's another hypothesis, this is the first other one. So we say, okay, this is our claim, and they claim that kids ages 0 to 2 spend an average of 29 hours per week in care not provided by their parents. So they're saying that the average for all kids, that is equal to 29 hours per week. And I'm just going to write 29, but keep in mind that this is hours per week in care not provided by parents. Now, if this is the claim, well, then the opposite of this is, and this is the null. The null always gets the equals to sign. So you can always just write H naught, and naught is another way of saying 0. I know some of you guys haven't heard it that way before, but that's the way I'm really used to saying it. So we have H naught, and that's equal to 29, always gets the equals sign. And then the alternative is the opposite of this. So this one's going to be not equals to 29. And when we write this down, this tells us something important. This guy, the second hypothesis, the alternative, tells us how many tails. How many tails. So we see here that if it was like this or like this, it would be one-sided. But since we have a not equals to, we know that it is a two-tail test. So that's going to be important for when we use our alpha. So we've got that piece of information. Let's keep going. So 29 hours per week, and I'm going to start right here. A study was conducted with a random sample of 30 infants. So there we have our N. So I'm going to put that here. N is equal to 30. And it was found they spend an average of 32.3 hours per week in care not provided by their parents. So we have a new average now before our average. So I forgot to write something very important next to these, and that is what is this value, 29? Well, they're saying it's the mean, but not just any mean. They're saying that it's the population mean, mu. And so that's really important to have there. So you're going to want to write that they're claiming that the mean, the population mean is 29. And so we did a study and we found that they spend an average of 32.3 hours per week not provided in care not provided by their parents. So this would be a sample mean because it only applies for our study of 30 infants. So we're going to put X bar is equal to 32.3. Now keep in mind, Greek letters are generally population. And when you see English letters, those are going to be sample things. So we say not provided by the parents, the population standard deviation. And keep in mind here we have the keyword population. So that is going to be a sigma. And that is 3.5 hours. At an alpha, so let's write that down. Alpha is equal to 0.01. Is there sufficient evidence to conclude the mean differs? And so, okay, this is our data. We've sort of extracted it from the problem, and we want to know this deal. Now, after we have these things, we should draw out our our normal curve. So here we go. We'll just draw out and sketch a general curve. And before we do anything with this curve, we have to identify, are we dealing with a t or a z-score? Which one are we dealing with? Well, we know this by the kind of standard deviation. So it's determined by the standard deviation, by the kind of standard deviation. So I'm just going to write standard deviation. What do I mean by that? Is it a population or is it a sample standard deviation? Now, with the rules for sample, can be a little bit different for some teachers. Some teachers run by the rule that they only look at population or sample. Others look at how many samples were taken. Like if 500 samples were taken, they would say that justifies using a z-score. But in general, I'm going to follow just sort of the most broad rule here. So if it's a population standard deviation, we're going to use a z-score. And if it's a sample standard deviation, we're going to use a t-score. We were given a population standard deviation, so that means we are going to use a z-score. Now we come down here and we look at our alpha. The alpha is the area in the tail. And with an S, tails. Possibly it could be more than one. We know that it is more than one because we found out up here it is a two-tail test. So we have a tail here and a tail here. And there's some area in each one. And we're splitting this alpha into two pieces. So this part has alpha over 2, and this part has alpha over 2. So if it's got alpha over 2, right, this is going to just be 0.01 divided by 2. We can just do that on a calculator really quick. We just turn it on, 0.01 divided by 2, and we get 0.005. So this is 0.005, and this is 0.005. That is the amount of area that is there. Now, the way this works, right, is they're claiming that the mean is this thing, right? So they're saying that the population mean mu is right here. And they are 99. We are doing a test to be 99% sure. So if our study reveals that the mean is actually way out here or way out here, that is so far away from what they claimed. This is the mean they claimed, mean claimed. If it's this far away, this is so far away that if it is out there, we say that this thing, the mean that they claimed, has got to be wrong. There's just no way it's right. It's like, it's way too far off. That's the idea right here. So we say, okay, we need to find out the z-scores that go to these. So we have a z1 and a z2. Now keep in mind, these are symmetric. z1 and z2 are symmetric. So we actually just need to find one and then just take the plus. The plus is on the other side. Just take the plus and the minus of whatever that z-score is. So, okay. We know that it corresponds to an alpha of 0.005, and we can find that on the chart because this is the area to the left. So it's easiest to just look this one up. So we're going to go ahead and go to the chart on a z table because we found out it's a z-score. All right, let me get the calculator out of the way. So we have a area of 0.005. Now remember, areas are here in the middle, and we can find an area and go backwards to get a z-score, which is what we are going to do. So we know that 0.005 is less than 50%, which means that the z-score is going to be on this side, so it'll be a negative z-score, right? This side has the positive z-scores. So that means that we're on the right side to look at because this is negative. So we want 0.005. We just need a number incredibly close to this. You don't have to totally nail it. You could pick the very closest one or one just super, super close to it. So 0.005, let's see if we can't find that. And so we're looking in the middle here, and we're going to work backwards, right? Because these values are the areas. So we say here's 0.0055. That's all right. We can get better than that. And over here, it looks like we get as close as we're going to get. 0.00508 or 0.00494. They're both pretty close. This one is slightly closer, so I'm going to pick this one. But if you picked this one, you know, you'll still have a really, really close z-score. It's not going to be super duper important as long as you're incredibly close. So if we look at this and go backwards, that corresponds to a z-score of negative 2.5, and if we come up, 0.08. So our z-score that goes with this is negative 2.58. And remember, it's symmetric. So the same z-score on the other side will correspond to just the positive version of that. So if we come back to our chart here and we look at this, well, if we've got a lower z and an upper z, the lower z is going to be negative 2.58. So we have our negative. And then the other side is just going to be the positive of that, positive 2.58. And you could justify it on your paper by saying by symmetry. And so if your teacher wants to see your reasoning, you could write by symmetry. That's why this is true. And now we've got our two z-scores. Now what we need to do is compute a test statistic. So this is looking a bit messy. Let's go ahead and just clean this up a bit and just write it all like this. We'll move these up here and these up here. And we know that this is 0.005 and this is 0.005. So, okay. And we know that it's by symmetry for the z-score. Now we're going to find the test statistic. So the test statistic, that's a z, well, that's going to be equal to, and keep in mind, remember your formula, x bar minus the mean. And remember, it's x bar because our claim is dealing with the average. And we have a mean. So it's not regular old x, it's x bar. All right, and so with the x bar formula, we also have our standard deviation, and that is divided by the square root of n. Now, these are all values that we have. We were given these. This is the claim value that they have. This is our computed value, the one that we found from our study. And then we were given this, and this is also from our study, n. So let's go ahead and just plug these in. So this thing, when we plug it all in, we're going to get z is equal to x bar. Our x bar we found to be 32.3. It's going to be 32.3 minus the mean, which the mean they claimed was 29, right? The population mean. And that's going to be over sigma. Our sigma is 3.5 divided by the square root of n, which is 30. This is going to be equal to something. Let's figure out what that is. So let's grab our calculator. All right, and we're going to turn our calculator on. Now here we've got a fraction right off the bat, and so we're going to pull up the fraction menu. To do that, we want to hit the F1, and that's green. So we're going to hit green, F1, and we're going to choose the fraction, numerator over denominator. So we're going to choose 1. And the top's going to be 32.3 minus 29. Then we're going to go down to the bottom. And we have another fraction, so we're going to type that first. So we're going to hit the green button and then F1. And we're just going to choose the first one. And we have 3.5. And now we have a square root. Square root's right here in blue. And so over the squaring key. So we're going to hit the blue key and then the squaring key to get to the square root sign. And we're going to choose 30. And that is all you got to do. And we just hit enter. And we get a z-score of 5.164, which this is extremely big for a z-score. If you've done very many of these problems, anything past 3 is going to be a pretty big red flag that this is probably wrong. So let's go ahead and map that on there. So what this is saying is we took our mean and we subtracted off theirs, right? So if our mean is really, really close to their mean, like if our mean was also 29 and they had 29, well, that's 0. And when you divide by this, it's still going to be 0. And that would put us right here, smack right where they were. So we'd say, oh, you were really right. But if the number gets big, then we say, this looks more and more wrong. And look at this, 5.16. That's like way out here, right? So here's like 0. Here's 2.58, basically 3. We're way out here at like 5.164. So this is called our test statistic, right? Because we did a test and we're just comparing it. So this is our test stat. And we find that, whoa, this is not right. We are much, much higher than this. And so we would say, based on this, based on the fact that we're so far away from the mean, that this thing is not right. And so we would say, we would reject this. We would reject HO. We would reject the null hypothesis. So we'd say reject HO. And then we didn't talk about it, but we need to identify which one's the claim here. So the claim, right? Well, here we have the claim. They claim that this is the case. So the claim is not the same. This could have been the claim for all we know. So in this case, this was the claim. So here's our claim. And so we'd say we reject HO, and then there is not, according to our study, our study produced evidence, right? Because we went out, we did a study ourselves, and we found that it's this. And this is our evidence. This is evidence. And we did not produce evidence to support the idea that this is correct, that their original claim is right. So we would say that first we reject their null hypothesis, and then we're saying there is not sufficient evidence, sorry if I'm spelling this wrong, evidence to support the claim. Now, some teachers want you to write out what this claim is, because support the claim doesn't necessarily show that you know what the claim is. So you would say there's not sufficient evidence to support the claim, and then you would add on that kids ages 0 to 2 spend an average of 29 hours per week in care not provided by their parents. So you would add on like all of, basically you would just write everything that's up here, because that's what the claim is, right? That's what they claimed. So, okay, that's what we found here. So we found out they're probably wrong. Now, the reason we say there's not sufficient, or some people write there's not enough evidence, is because maybe we do another study and we find a number that's much closer to 29. Maybe we find that hey, you know, this number seems to be correct. We would do more studies to be more sure. And so just based on this one study, we didn't produce evidence that supports it. So we don't say that the initial claim is wrong. We just say, based on the evidence we produced, it's not enough to support it. And for that reason, we reject it. So it's sort of this logical train of thought. Because if you say, oh, based on this, it's wrong, what if we did another study and we find out this could be right? So we're not in the right to be able to say that this is necessarily wrong. So that's why we say it like this. It's sort of just a logical thing. Now, let's go ahead and find these same values doing it using the calculator method. Now, the calculator method is really great. If we come in here, we'll just go ahead and turn it on. If you go to stat, we already know that our z, we're using a z test. And so we're going to come over to tests, and then there is a z test right here at the top. So we're going to click that. And we don't have data, we have statistics, right? We were given the mean and the standard deviation. These are statistics. So we choose the stats version. And we go over here and we say, well, what's our mu naught? What was the original population mean claim? Well, that was 29. It's being covered up. Let me move up. That was 29. So we choose 29. Our sigma, well, sigma is simply, where are you? Oh, I read it right here, 3.5. And keep in mind, these are in hours, right? Our x bar, 32.3, 32.3. And our n is 30. So they need this so that they can do this formula for us, basically. They also want to know, hey, what was the alternative? We say it's not equals to. And the reason they need this is so that they can compute this z-score. They're doing that so that they can do basically what we did with the chart. And now we're going to hit calculate. And here it is. So for these conditions, they find a z of 5.164, which is exactly what we got. And this p-value expresses the area under the curve. So they're saying that the area under the curve is 2.4186, blah, 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 e to the negative 7. What does that mean? Well, that means that there's actually 6 zeros. When it's negative, you subtract 1, and that's the number of zeros. So it's actually let me write it out. The area would be 0.000, that's 3 zeros, 4, 5, 6, and then the numbers start 4, 1, 8, blah, blah, blah. This is the area. It's super, super, super tiny number. It's like way over here, like this little bitty area. That's like all it covers going off that way, right? And so this is super within the area of rejection. So I call this the dark region. This is the land that Mufasa told Simba to never go to. He said, do not go towards the dark land because that's where you reject the null hypothesis. So we're way, way, way inside that. So if they said use a p-test, you would say, well, this p-value is way less than the alpha. And so, because think about it, if p is bigger than alpha is 0.005, it would be outside over here in a region that's not being rejected. And so if p is greater than alpha, that's the same thing as just getting a test stat that falls within this region. So they're connected to each other. So this is just using areas instead. So we say, oh, well, this is less than alpha. So it's got to be in the rejection region because that's what alpha is. It's the rejection region. And so we reject the null hypothesis. And then we look on here and we say, oh, well, that's actually pretty much all we need. So then we could just draw the same conclusion. We could say, based on the fact that either p is less than alpha, or based on the fact that our z-score 5.164, blah, 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 is way off in outer space. It's way over here in the rejection region. It's not in the region that says that this is right. So we would reject HO, and then again, we'd say there's not sufficient evidence to support the claim that, and then you would state the big long claim. Now we can do this same thing in Excel. Excel actually has a z-test function, but it requires data in order to use. So what we're going to do is we're just going to find the values necessary, and we're going to use the formula. So what we would do is we would come into Excel. So we'll go into Excel, and the first thing we need is the z value from alpha. So we knew that our alpha, when it's two tails and we split it in half, so half is below, half is above, and it had an area of 0.005 to the left of it. So we're just going to type in equals to let it know that we're doing a equation. In fact, let's label this first. So this is going to be our z-score for alpha. So in order to get the z-score, we actually need to use the inverse function, right? Because normally normal distribution gives us the area. We want to go backwards, and that's to invert the process. So we're going to type equals, and we're going to type normal dot inverse, INV. Now alpha is really a probability. It's the chance that the population mean is really all the way out there, and basically where we say this is as far as we're allowed to go, but we are expressing it as a very small chance. That's why we want alpha to be very small. And so we know that alpha for one tail is 0.005. Now the mean is a z-score mean. Okay, it's not the mean from your data set, because we're dealing with z-scores here. So remember, z-scores always have a mean of 0 and a standard deviation of 1. We hit enter, we get our negative 2.57, yada, yada, yada. And we know that we're going to have the positive and the negative version of this. So that's going to be this, and that's by symmetry. And then we're going to go ahead and find our test statistic. And so we can actually just type it right into Excel. I actually recommend probably just using a calculator for this. It might be a bit easier. But in Excel, you can type parentheses, because we want to do the top part of the fraction first. That's going to be x bar, which is 32.3 minus 29, close parentheses. Then we're going to divide open parentheses, because the whole denominator's got to be done separately. So we put it in its own parentheses, 3.5. And then we want to divide 3.5 by the square root. So you get to square root. Oh, we should put an equals at the beginning to let it know we're doing a function. We're doing some calculations. So we want the square root. Yeah. Square root. And then you open parentheses of the number. So the number we want the square root of is 30. And then we close the parentheses for the square root. And then we close the parentheses for the denominator. And we hit enter. And we get our z-score. So I'm actually going to put this here. And this is our test stat. And then remember, we have the positive and the negative. So there's actually a flipped version of this. That's 2.57583, on and on and on and on. And we would say, well, this is much bigger than this. So we are going to reject the null. There is not sufficient evidence to support the claim. But you would have to draw this out on your paper like we've done so here. This is just how you would get the same values using Excel. So hopefully that clears things up. That's a variety of ways. There is one other thing I should mention. Some teachers want you to use the calculator to find the value, but they do not want you to use the z-test. They want to see you do it by hand, and because doing it by hand really shows you know what you're doing. So if you pull up the calculator, there is another way to get this z-score that does not require the chart, and that's to use the distribution like we just did in Excel. So you can go ahead, turn it on, go to second distribution, and in here there is a inverse normal, just like we had the inverse normal in Excel. You're going to click this. The area we want is in one tail, and then we'll just take the positive and the negative by symmetry. And then we have a mean of 0, remember, because it's a standard normal distribution, mean of 0, standard deviation of 1. And we hit paste, and we get the same thing. So that's the way to get the z-score, and then you can use the calculator to do this. And that is that. If you have any questions about this, let me know. Subscribe, and we will see you in the next problem.